All right, kiddos, we're going to do a quick review. Part of this review is going to sound really familiar because we just did it in class, but the people at home didn't get to see any of that, right? Also, it doesn't hurt to hear it more than once. Parts of the whole. The first thing that I asked all of you to write down when I walked around, I noticed most of you wrote this down somewhere, is that the sum of the parts is equal to the whole. Give me a thumbs up if you wrote that down. I hope you wrote that down because that's like the crux of this entire portion of this unit of states of matter is the sum of the parts is equal to the whole. And we went back to yesterday and we talked about the goldfish that we had. And Jesse, we said in our goldfish cup we had 34 grams or something similar to that, right, of goldfish. I weighed them, 34 grams. But then I took them and I crushed them into teeny tiny, like sand, right? They were like tiny little bits of goldfish. It didn't even take up as much space in the cup anymore. And some of us said, oh, less space, less weight. And we were wrong. Some of us said, well, there's a lot more pieces now than you had before. It has to weigh more. And we were wrong. And then some of us, it clicked immediately. Well, Mr. Bullens, you didn't add any goldfish. You didn't take any goldfish away. That should weigh the same, and we were correct. But we can't just assume that that always works that way, right? So today in class, the first thing we did is we took a Hershey bar and we weighed the entire Hershey bar. Now again, I didn't bring in the full Hershey bar that's in the background. Normally we do that, and normally we share the chocolate. Can't share chocolate right now with everybody in the classroom because you can't be touching and handing things around with their stomach bugs and everything else going around, right? But if we had a 1.55 ounce Hershey bar, now our Hershey bar weighed way less than that because it was like one of those mini bars. But even when you break it into these little bitty pieces, I know that there are some people that are still kind of confused, like, Mr. Bullens, you have more pieces, it's going to weigh more. Or you say, Mr. Bullens, if you break the Hershey bar into like smaller pieces, it's smaller, it's going to weigh less. Luckily, and I think today in here, a majority of you are saying, no. Like, you're not tricking me with that anymore. It's the same Hershey bar, it's just broken into smaller pieces. When we broke it into 12 pieces, it wasn't more, it wasn't less, it weighed the same. And the reason why it weighs the same, because the sum of the parts is equal to the whole. Give me a thumbs up if that's starting to like kind of click in your head now. I think it is. For me it is, at least. It's starting to be like, okay, I've got this. This is really not a big deal. So we broke it into little pieces, which is fun. I did not do this. I learned my lesson last year. We're just going to talk about that in here this year. What if I brought in like a grater and I grated it into fine little pieces of chocolate? Y'all had ants everywhere in the room. There was chocolate. It wouldn't go away. Like, it took a long time to get all that chocolate up. It was a huge mess. I'm not doing that again. We can look at the picture and pretend we grated it into tiny little pieces. But even if you do grate it into tiny little pieces, if you had a 1.55 ounce chocolate bar and you grated the whole thing into the bowl, and I did it last year, and boy, were the kids mad because the whole hall smelled like chocolate. It smelled like chocolate everywhere. But it's still 1.55 ounces because even all of those teeny tiny little pieces are still equal to the whole, aren't they? We're not going to do this in class because this would make it, if grading it made a mess, I can only imagine what this would have done. But if we melted a 1.55 ounce chocolate bar in class, we could do that. We're not going to. But if we did, it's still the same amount of chocolate, right? Just in liquid form at that point. You would have 1.55 ounces of chocolate. It would just be in liquid form. Because again, the sum of the parts is equal to the whole. I only got a couple people that are logged into this, but if you're looking at this, select all the answers that apply, and we're not going to log in because we don't have time for that. Melting and collecting the syrup is the same as the candy bar. Breaking it into pieces is the same as the candy bar. Shaving the bar into tiny shavings is the same as the candy bar. And breaking into pieces and eating 3 pieces does not work out, does it? Because now I've actually taken some pieces away, haven't I? You can't break it into pieces and then take 3 and it still weigh the same. That would be a magical candy bar. That doesn't work out that well. And Fabiana would share it with us, wouldn't you? If you broke it into pieces and we ate some but it was still the same. Just handing out candy bars all day, right? Be awesome. I gave Fabiana some, well, they're not Legos, but I gave her some Unifix cubes because I think Grant took all the Legos home. Knucklehead. But she had like 33 grams of Unifix cubes. You put them together into a shape, and guess what? It still weighed the same, right? I don't think that's a surprise to anybody. We actually did more than 10 grams of salt and 10 grams of water, but if we had done 10 and 10, we got 20, correct? Every time we did something, the sum of the parts was equal to the whole. However, this is the one that got us, a few of us, right? Some of us in here, about half of us got confused when I put on the board this problem here. Because, again, this is a very easy mistake to make. And Veda, I probably would have made this mistake. Honestly, like, every time you give me some numbers, 20 grams of salt, 20 grams of water, the answer is 40, Mr. Bullen. It's like, come on, give me something hard. And then I give you this. I'm like, that's easy. 10 plus 20 is 30 plus 15 is 45, and I'm done. I understand why kids did that, but they didn't think about it like this. There's definitely 10 grams of cheese, right? Here's the 10 grams of cheese. There's definitely 20 grams of ham. There's the 20 grams of ham. And you're thinking, but Mr. Bullen, 10 plus 20 is 30 plus 15 is 45. How are you saying that it's different? Because it's 2 slices of bread. So if you put those 2 slices together, you get a different answer. And a good portion of you in here actually got the correct answer, that your sandwich would weigh 60 grams, right? Those of us that missed it, those of us at home that probably missed that same thing as well. Do you understand how we got to that answer? And we're not going to get tricked again, correct? Hopefully not get tricked again. We'll see how that goes, though. We don't need to do that. I am going to try something, though. Unfortunately, you'll just have to kind of look at the background there, and then we'll come back and talk about it online. But I'm going to take a 7-gram Alka-Seltzer tab and add it to a 280-gram bottle of water. So again, I'm not trying to be mean. I'm not trying to trick anybody, but I do want us to learn this lesson. When I put the 7 grams of Alka-Seltzer in the 280 grams of water, we all saw it fizz, very similar to this, right? And we said, well, Mr. Bullen, you've been doing this all day. This is easy. 280 plus 7 has got to be 287. And I understand why you wrote that. But that is not 287. It's 285. And I want to talk to you about why it was 285. What did you notice was happening to that Alka-Seltzer tab when I put it in the water? What did it do, Glenn? And what else was it doing? It was releasing a gas, wasn't it? Could I trap the gas inside of that system? No, the top is open. The top is open. I can't, the gas is not, it's going to like go out into the atmosphere. So that brings up 2 new words that we're going to talk about today. Open systems versus closed systems. And they are exactly what they sound like. An open system is a system where energy or mass can be lost to the environment. When I had that open system, was the gas allowed to escape out of the top of that system? Yes. That is called an open system. If I were to find a way to close the top of that, I'll see if we can do that in a moment, the gas would not be able to escape. And it should stay 287 if the gas can't escape. And we'll see if that will work out here in just one moment, because that is a closed system. All right, so we just went back and retried our experiment, except instead of having an open system this time, even though I kind of failed to begin with there, we put the Alka-Seltzer into a different container that I was able to seal the top off with a balloon. We all know gas was trying to escape, right? And well, the gas eventually escaped because it popped the balloon off the top of the bottle. But we saw the balloon start to blow up. And some of you were saying that the balloon was moving around. Who could tell me why the balloon was moving around? What was causing that to happen, Veda?
The gas
the molecules of the gas, although I can't see it, I know it was moving around because the balloon was like wiggling around in the air because the gas molecules were trying to escape up and out of that closed system. So again, open system, a system in which mass or energy can be lost. To guess what a closed system is? A closed system is a system where it cannot be lost. So again, as we go back and kind of look at that, we know that the open system, we had mass loss, right? Gas was able to escape. We know that gas has mass. That's part of solid liquids gas. And then in our closed system, we were able to trap that into the system so the gas did not escape. And we realized in that instance that the mass was conserved and it stayed the exact same. All right, so I'm going to spend a little bit of time explaining some stuff to people at home, and then we're going to spend a majority of the next little bit working on our projects, which we should be getting finished with. I know that people in here don't have it because I didn't hand it out yesterday, but I know that I spent a little bit of time going over this with you yesterday, right? We talked about, yes, you must not have been paying attention. We didn't talk about this yesterday? All right. So, you have a rubric, but I want to talk about what it looks like to turn in different projects. And you can look at this scale here, and you can tell me what type of project you want to turn in, and we'll describe this a little bit more. But if you went to Starbucks and you got the wrong drink entirely, would you send it back? Yes. So if you give me the wrong project and you don't do a good job, I'm going to send that back. If you get some of the stuff on the project right, do you think you're really going to get a good grade? No, you will not get a good grade. I will probably give it back to you, be like, hey, you missed a bunch. Thank you for putting some things on here, but you missed a whole lot. Is it possible for you to go to Starbucks and get the drink right, and that's it? Yeah, I mean, that's typically what happens. You get your drink and you leave. That's a good experience. But a great experience is if, like, you get exactly what you ordered and some, right? Maybe they put extra whipped cream, extra sprinkles, whatever that is, or they made too much and they give you a little smaller cup of the extra stuff that's left over instead of throwing it in the trash. Wouldn't you be like, wow, holy cow, that's even better than what I expected, right? All of that is explained in this rubric that I will go over with you in class as well. But again, here are the things that should be on your project. You better somewhere in your project have listed and defined solid, liquid, gas. Well, duh, the three sides of your project are solid, liquid, and gas, right? Within your project, you need to talk about melting, freezing, evaporation, condensation, sublimation, and desublimation. But we've covered all that, right? Remember the triangle that we drew in class? It covers all of that. You need to somewhere in your pictures have like what the molecules look like and describe that. Does that make sense? Okay. You need to tell me how a substance can change from solid to liquid to gas, or from gas to liquid, or from liquid to gas, and so forth. Again, I would use water, Shayla, in every one of my examples for certain because that's the one we see changing states the most. And last but not least, if you talk about something, you better draw a picture of it. Make sense? All right. Hopefully that makes sense to the people at home. And again, for the people at home, I've given them their explanation here, and I've even given them an exemplar page here of what their slides should look like. Again, if you get sent home, hopefully you take your piece of paper home and you can work on it, or you come by and pick it up one afternoon, or you send it home with your little sister, whatever we happen to have to do, right? And you have your paper at home that you can work on, but if you happen to be working online, then this is what it would look like online. Good? All right, so we're spending the rest of our time working on our project. I'm going to